So we're asked what is the maximum weight the system can support if the average normal stress in each wire is not to exceed 200 megapascals. The diameter of AB is 5 millimeters and the diameter of BC is 7 millimeters. So there's a few different approaches that you can take to solve this. So I'm just going to demonstrate one of them. And the approach that I'm going to take is first of all looking at the forces in each of these members, BC and AB, as a function of the weight applied. Okay. So once we have expressions for the force in each of those wires, what I'm going to then look at is the stress in each of these wires. And because we have a limit on how big that can be, we should then be able to calculate the maximum weight that each of these wires can support. So that's my approach. There are other ways to do it, and of course, feel free to do them. I just think this is the easiest way. So I'm going to start with drawing my free body diagram, and I'm going to draw it of the hook that sits in the middle here. So we know that both of these two members are going to be 2 force. That's because they're pinned on either end, and we know that for 2 force members, the direction of the force is in the direction of the member itself. So the force applied onto the hook through this wire is going to be like this, and it's applied at the angle of 20 degrees as we're given in the diagram here. Similarly, this one is going to be applied at an angle of 50 degrees, the same as the member. So this is 50. So I'll call this one FBC and this one FAB. The only other force that's going to be on our little hook here is the weight pulling down, and I'm going to call this W, and that's the one that we need to determine to finish this question. So now that I've got my free body diagram, what I want to do is calculate the 2 forces here in terms of the weight applied. So we have our equilibrium equations to help us out. These 3 here, and we can kind of think about what order we want to apply them in. So the first one is sum of forces in the x direction, and if we apply that, we're going to end up with the 2 unknowns in the equation, so it wouldn't be solvable directly. Same thing's going to happen for summing in the y direction, because we're going to end up with these 2 forces in the equation, so it's not directly solvable. The last option we have is to sum moments to be 0, but unfortunately for this one it's not really going to help us out because the most obvious place you would sum is like the center here, and all of these forces are going to have their line of action going through that point. So if you sum moments, you're going to basically get 0 equals 0. So that's not going to be useful to us. So unfortunately it becomes a case of needing to apply these first 2 equations and solving them simultaneously. So let's start with summing forces in the x direction to be 0. So we're going to have a negative component from FAB, and it's the sine side of the triangle for the x component. Remember that because we've been given the angle with respect to the y-axis rather than the x, it's going to be different to most situations. But anyway, the opposite side of the triangle gives us the x component this time, so that's why we're using sine. And same thing for this one, we need the opposite side of the triangle. This time it's going to be positive x direction. It's BC, sorry. And this of course doesn't have a x component, so it's not in the equation. So I'm going to rearrange this one to substitute in its next step. I'm going to choose to rearrange for FBC, but it doesn't really matter. So this goes to the other side of the equation and becomes positive. And then we need to divide by the sine 20. So that's going to be equation 1. So our other equation comes from summing forces in y. So we're going to have a part of FAB going up, and it's going to be the cos side that we need to take. We're going to have part of FBC going up. Again, it's going to be the cos side that we need to take. And then we're going to have this force acting downwards. It's completely in y, so we just throw it in. And this becomes equation 2. So it's now a case of solving them simultaneously. I'm going to substitute equation 1 into equation 2. So go going through this. So FBC gets replaced with this up here. And now we have an equation where there's only one unknown in terms of the forces, so that's FAB. So I want to put these two terms together. So putting all the constants in your calculator, you can work out that this comes to be 2.747 times FAB. And I'm moving the W to the other side. So I can conclude that FAB is going to be equal to W divided by this, which is the same as 0.364 times W. Okay, so once we know the weight in here, we would be able to calculate directly the force through that wire. So we want to know what FBC is in terms of the weight as well, and we can do that using equation 1. So FBC is equal to FAB, which we just simplified to this, times these sign things. And when we put together all these constants again, it becomes 0.815 times W. Alright, so now what we need to do is look at the stress. So we were given a condition for the stress. We were told that our normal stress cannot exceed 200 megapascals. We were also given the diameters of each of our wires, which is going to help us with this calculation. So I'm going to start with looking at member AB, and we know that the stress in the wire is going to be equal to the force in it divided by the cross-sectional area. So we were told that's 200 megapascals, so that's going to go in for stress, and I'm going to put it in megapascals. I'm going to use force in newtons, and I'm going to use area in millimeters squared, and those units all work together. Take a look at the recap video if you want to know a bit more about that. So the force here in AB we just worked out to be this 0.364 W, and the area, so above we had a diameter of 5 millimeters in this wire, so it's going to be pi on 4 times 5 squared in order to get the area, remembering that if you have a circle with a diameter, this is how you calculate the cross-sectional area of it. Alright, so in this equation that we've just written out, the only unknown is W, which is the weight. So if you rearrange for it, it becomes 10789 newtons. Okay, so now we just need to look at what's happening in BC and double check what it can hold, or the point at it starts to exceed its stress criteria. So again, we can use our equation where stress is equal to force divided by area. A bit dodgy. So again, we have a limit of 200 megapascals that we need to apply. We've worked out the force in BC. It came to this as a function of the weight. And the cross-sectional area is dependent on this 7 meter diameter, for this one. So it's pi on 4 times 7 squared. And rearranging for W, we find out that this one can support 9442 newtons. So we weren't asked exactly what weight each wire could hold. We were asked what the system could hold. So we need to decide which one kind of controls the system. And the answer is going to be this one here, because it can only hold a smaller amount than what this one can hold. So this is like the limiting factor. So I would conclude this question with system can hold maximum of 9442 newtons. If we tried to hold up to this much, the first wire, BC, would have exceeded its stress limit at this other weight. So that's why we're just picking the minimum value of the two for the overall system. So that concludes that question, and see you in another video.